This session we are going to talk about microstrip antennas. Microstrip antennas are one of the most popular antennas in the wireless communication market, and we can find applications of microstrip antennas in various fields of the high-tech technology, like in mobile communication, in our cellular phone, in satellite communication, either in fixed antennas or fixed application or mobile application, missile telemetry, biomedical uses, or radar systems. Microstrip antennas received considerable attention starting in the 1970s in a paper written by Robert Munson, and although the idea of microstrip antenna can be traced back to Deschamps back in 1953. The major advantages which makes the microstrip antenna so popular are they are low weight, low cost, low profile, and they can fit any shape, therefore they are conformal. Microstrip antennas are also very easy to fabricate and can be integrated with other microstrip components in monolithic application like RFIC or MMIC. However, they have also some drawbacks. The drawbacks which I'm going to talk about are initially when the microstrip antenna have started to be present in the market, but some of them have been minimized dramatically. The major drawback of a microstrip antenna is its low frequency bandwidth, and the reason for the low frequency bandwidth of the microstrip antenna is actually because of their physical basic concept, which is based on a resonator type. These drawbacks actually have been minimized in the recent years, and we can obtain, as we'll see later on in the presentation, even microstrip antennas which can cover even 70 to 80%. When I'm talking here about low frequency bandwidth, we are talking about 4 to 5% bandwidth. Another drawback is their relatively low radiation efficiency as we go up in frequency, or when the antenna array size increases. And this is due to the increase in the feeding network losses, which increase as the lengths of the feeding lines increase, and also with the frequency. Again, this kind of drawback can be traced back to the initial design of microstrip antennas, but in recent years also significant breakthrough have been done also on this drawback, and we can see today designs with based on waveguides or hybrid waveguide and microstrip lines or parallel plate waveguides in which the network losses have been minimized dramatically, and we can obtain high efficiencies even at very high frequencies up to 30 or 40 gigahertz. Another drawback of the microstrip antennas is that they're relatively low power levels that they can confine because there is a danger of breakthrough between the patch antenna and the ground, and therefore they cannot fit very well for application like high power radars in which we try to transmit kilowatts or megawatts. So we are talking here about an antenna which can operate very well in the hundreds of watts and a little bit above, but not very high power. Now let's see how we can understand better their radiation concept. Basically, the microstrip antenna concept trace back to the microstrip line, which we can see here, okay? And here is the field distribution in the cross-section of a microstrip line. What is interesting to know that even the microstrip line is able to radiate, and we can actually model the radiation from a microstrip line as equivalent from two radiating slots on each side of the strip here, And in the microstrip line, actually, those two radiating slots are opposite, the electric field in those two radiating slots is opposite in direction, and therefore we get a minimum radiation on an axis, which is normal to the substrate. Therefore, a microstrip line is not so beneficial in terms of transmission because it transmits null on a normal axis to the microstrip. In a microstrip antenna, actually, the effect of radiation from those equivalent radiating slots is used in a more clever way. In a microstrip antenna, we actually have again a microstrip, but which is open circuit on both sides of the microstrip line. And the two radiating slots equivalent at the edges of the microstrip lines, there are excited in phase, and then the radiated far field on an axis which is normal to the antenna, they actually combine in phase, and we obtain enhancement of the radiation. In order to obtain actually that the two radiating slots are combined in phase on an axis normal to the antenna, we need to get some sort of the distance between those two radiating slots has to be lambda over 2. Now, another way to look to this device is actually to consider this microstrip line as a transmission line which is open on both sides, and therefore we obtain here some sort of resonator. And this resonator develops inside a field distribution, and therefore it actually has the features of a resonator, and it is some sort of resonator which is leaking from its edges. Here we can see the equivalent radiating slot, which can be actually, which models actually the radiation from the two from the two edges of the microstrip. The microstrip is fed at some location inside the microstrip antenna, and this is the way that we also control the input impedance, as we'll see later. Few words about feeding methods. Since the microstrip antenna is some sort of a resonator, we need somehow to excite the fields in this generator, in this resonator. And there are various ways to feed the antenna. The most common way is basically to use a coaxial probe, as we can see here, in which a probe is actually penetrating the ground plane and is short circuited to the upper conductive of the antenna. By the way, the upper conductive of the antenna is also called a patch because it can actually have many shapes, and in this slide we actually see only rectangular, but it can be of any shape essentially. So a second way of feeding the resonator or the cavity domain under the patch is using some sort of inset microstrip into the cavity. And a third way is using a strip which is penetrating the cavity domain under the patch without touching anything, and by electromagnetic coupling it actually excites the cavity domain under the patch. A fourth way, which is used also for feeding microstrip antenna, is using a microstrip line which excites a slot, and this slot is actually exciting the cavity domain under the patch antenna. This this feeding is appropriate for multi-layer applications, while in which we don't want to use vias from one layer to another layer, and therefore is popular especially for multi-layer application in which we actually integrate RF circuits with antennas. Now let's talk a little bit about some analysis models of the microstrip antennas. The model used for microstrip antenna analysis are the transmission line model, which is the most simplest and the first to be published in the literature, the cavity model, and the full wave analysis, which is the most accurate and rigorous type of analysis. And for the full wave analysis, actually, we can also distinguish three different approaches. One is based on the green function formulation, with which we actually formulate an integral equation, and the solution of this integral equation is done using the method of moments. The second approach for the full wave analysis is solution using the numerical method of the finite difference time domain, FDTD, in which we actually solve Maxwell equation numerically. And the third one is also based on a numerical solution of differential equation, but the solution is based on the method called the finite element method, FEM. All three methods are today actually have been implemented, and one can find commercialized software which implemented the three approaches, such that, for instance, the integral equation method can be found in a software called IS3D by Zealand. The FDTD can be found in a software called the MicroStudio from CST, and the finite element method can be found in a software HFSS by ANSYS. The importance and the advantage of the full wave analysis is the fact that they can analyze any type of microstrip antenna without any limitation, while on the geometry or the configuration, while the two previous, the transmission line and the cavity model, are actually limited by some limitations, as we'll discuss later. However, of course, the full wave analysis is much more complicated to be implemented, and in simple cases, we may use the transmission line model and the cavity model because they give some sort of insight into the problem, which helps to the designer before he gets into the more complicated type of analysis. So let's start now with the transmission line model. The transmission line model was introduced by Munson in 1974. It is applicable mainly to rectangular patch antennas, and models the patch antenna as two radiating slots connected by a microstrip line with a W, as we have seen before. The advantages of the transmission line model is that it is simple and it's computational efficient. However, it does have some drawbacks. And the first one is that it does not account for higher order modes that may be excited in the patch cavity domain, as we will see later. It assumes substrate thickness that H, which is much, much less than the wavelengths, in order to avoid surface wave excitation in the substrate that supports the patch antenna. And it is unable to analyze multi-layer patch antenna elements like stacked patch and many other shapes of patch antennas, which cannot be modeled in a simple model like the transmission line model. Now let's talk about the computation of the radiation pattern. The radiation pattern of using the transmission line model is done by considering the radiation from equivalent two radiating slots on both sides of the patch antenna. Those two radiating slots are equivalent also to two magnetic currents, equivalent magnetic currents, and here we can see the field, the electric field, in which we actually combine the radiation from the two slots. V1 and V2 represents actually the excitation of each one of those slots. If V1 is equal to the negative of V2, then we obtain actually combined radiation if the distance between the two radiating slots is actually obtained if the distance between the two radiating slots is equal to lambda over 2. In case that this condition is obtained, that V1 is equal to minus V2, this is the radiation pattern. This is the radiation function of the patch antenna, and here we can see typical radiation pattern plots in the E-plane and H-plane. What we can notice actually here, that the patch antenna with rectangular shape is pretty wide in beam width, and in both E and H plane, and the 3 dB or half power beam width is approximately 70 to 80 degrees. And therefore, a patch antenna can be used actually either as a single element or as an element in an array in order to obtain or to control the radiation features of a larger antenna. Now let's talk about the impedance computation. Okay, the model for the model in the transmission line model analysis is based on a very simple transmission line with length L, which is equivalent to the length of the patch or the microstrip antenna, and we can also observe here two loads on the transmission line. One is related to the radiation, which is G plus JB due to this radiating slot, and another G plus JB representing the radiation losses of these radiating slots. In addition to that, we have here two dependent current sources, which G1V2 and G12V1, which represent actually the coupling between those two slots. So if we want to compute the input impedance at any point along the axis of the microstrip antenna, we have to analyze a very simple circuit, a transmission line circuit, as shown here. For that, we need a few parameters, and those parameters are, first, the characteristic impedance of the transmission line, given by this expression, the propagation constant of the transmission line, the effective dielectric constant of the cavity domain or the microstrip line of the antenna, and delta L, which represent the width of those two equivalent radiating slots on both edges of the patch, and B, which represent actually the effect of the reactive near field very close to the edges, and this is equivalent to an expression of an equivalent transmission line open circuit. And the last parameter to be on this review of the general parameter is the resonant frequency, which is obtained basically when the total length of the microstrip antenna is approximately lambda over 2, half wavelength. For that length, actually obtain that V1 is equal to minus V2, and therefore we obtain combination of the radiation from those two radiating slots. Now, to the computation of G, which represents radiation losses, G12, which represents coupling between those two radiating slots. In order to compute those two quantities, those two parameters, actually you use the electric and magnetic far fields computed previously by the radiation pattern, and they are equal actually the total input power to the microstrip antenna by separating or associating each term in this integral obtained by vector pointing to the three terms here. We can separate the derivation for the radiation resistance or admittance, sorry, and G12, which represents the coupling. For the simple case, or the particular case in which L is equal to lambda over 2, we obtain that the total input impedance at one of the edges is equal to 2 times G plus JB plus G12. So this is a very simple equation of a very simple formula to obtain the input admittance. Here we see actually a plot of the total of the input resistance and the input reactance of the microstrip antenna. What is interesting to note here that the reactance is actually going from positive to negative, which is typical to a resonant device, such that for lower frequencies we obtain inductive performance, and for higher frequencies we obtain capacitive performance. In this plot, we can actually observe how the input resistance of the patch antenna varies with the input feeding point location along the axis of the patch, such that on the edges we obtain maximum radiation resistance, and at the center the input resistance is equal to 0. This is a very useful way to control the impedance of the microstrip antenna by varying the location of the input, by varying the location of the feeding point.